Welcome to AI Frontiers, where we explore the cutting-edge developments reshaping our technological future. Today, we're breaking through the learning barriers with an exploration of 103 groundbreaking papers from computer science machine learning, published on December 21st, 2025. These aren't just incremental improvements. They represent revolutionary advances in machine learning efficiency and reliability. Featuring architectural innovations that achieve thousand-fold performance improvements, new approaches to uncertainty and robustness in AI systems, and the integration of domain knowledge with data-driven learning. This research comes from the world's leading AI laboratories and is fundamentally reshaping how machines learn and adapt. Today's journey takes us through AI innovation's most exciting developments, offering a deep dive into machine learning's transformative breakthroughs. We'll discover how AI systems are becoming dramatically more efficient, explore advances in making AI more reliable and trustworthy, and understand new architectures revolutionizing how machines learn. Our exploration examines real-world applications spanning from finance to earthquake prediction, while previewing the future directions that will shape tomorrow's AI landscape. This comprehensive analysis reveals how researchers are pushing beyond traditional scaling paradigms toward more sophisticated approaches emphasizing efficiency, reliability, and domain integration. Computer science machine learning represents the engine of AI progress, serving as the field reshaping our digital future. This domain encompasses algorithms that enable computers to learn patterns without explicit programming, drawing from an interdisciplinary foundation that combines probability theory, optimization techniques, and neuroscience insights. These systems power everything from Netflix recommendations to medical diagnostics, tackling uncertainty, decision-making, and pattern recognition at unprecedented scale. The field bridges theoretical foundations with practical real-world applications, forming the invisible backbone of virtually every modern technology we interact with daily. From autonomous vehicles navigating complex traffic patterns to medical AI systems detecting diseases earlier than human specialists alone could manage, machine learning research continues expanding into increasingly complex and demanding applications. The first major theme reshaping machine learning involves architectural revolution and efficiency breakthroughs, fundamentally reimagining how neural networks process information. Researchers are developing hierarchical processing systems that replace traditional token-by-token scanning with multi-resolution context access, achieving thousand-fold efficiency gains. The PHOTON architecture by Ichikawa and colleagues demonstrates this transformative potential, proving that quadratic scaling limitations are merely architectural artifacts rather than fundamental constraints. These innovations are democratizing advanced AI through resource-efficient designs that maintain competitive performance while dramatically reducing computational requirements. This represents a paradigm shift from brute force scaling toward intelligent architectural design that optimizes both efficiency and capability. The second prominent theme focuses on robustness in dynamic and uncertain environments, building AI systems that remain reliable under stress. Research on conditional adversarial fragility reveals context-dependent vulnerabilities that challenge our fundamental assumptions about model security. Babaskar and colleagues demonstrate that models become significantly more vulnerable during stress periods, showing that adversarial robustness is not static but varies with environmental conditions. This discovery has critical implications for AI deployment in high-stakes applications, from financial markets to healthcare systems. The findings necessitate adaptive security systems that can recognize regime changes and adjust their defensive posture accordingly, moving beyond static approaches to dynamic, context-aware robustness strategies. The third theme centers on uncertainty quantification and behavioral calibration, teaching AI systems to express their limitations honestly. This approach addresses the critical challenge of AI hallucination by training models to admit uncertainty appropriately. Wu and colleagues achieve remarkable results, demonstrating that behavioral calibration enables a 4 billion parameter model to match frontier model performance in uncertainty quantification. Using strictly proper scoring rules, researchers align model confidence with actual accuracy, creating a transferable metaskill independent of raw predictive accuracy. This represents a pathway to safer AI through epistemic honesty, enabling models to either abstain from producing responses or flag individual claims where uncertainty remains high, fundamentally changing how we approach AI reliability. Several critical insights are reshaping machine learning by challenging fundamental assumptions about model design and deployment. First, efficiency gains don't require performance sacrifices when proper architecture is employed, as demonstrated by hierarchical processing innovations. Second, model vulnerabilities are dynamic and context-dependent rather than static properties, necessitating adaptive approaches to AI security. Third, uncertainty quantification emerges as a learnable, transferable skill that can be developed independently of domain-specific knowledge. Fourth, hybrid neural-numerical approaches successfully optimize both speed and reliability for complex system modeling. Finally, domain knowledge integration enhances both capability and interpretability, creating more trustworthy and effective AI systems that leverage both data and understanding. Methodological innovations are driving progress through sophisticated approaches designed for complex learning challenges. Hierarchical processing captures multi-scale patterns efficiently by operating at multiple temporal and spatial resolutions simultaneously. Conditional variational autoencoders enable complex spatial temporal modeling by learning intricate correlations directly from data without requiring explicit mathematical formulations. Hybrid approaches combine mechanistic understanding with data learning, leveraging domain knowledge where available while maintaining flexibility for data-driven discovery. Graph neural networks with attention mechanisms excel at capturing relational information for problems involving complex structures and relationships. Reinforcement learning from human feedback incorporates proper scoring rules to align model behavior with desired outcomes, creating more reliable and aligned AI systems. Bhattaskar and colleagues' research on conditional adversarial fragility in financial machine learning reveals dynamic vulnerabilities in AI security that fundamentally change how we understand model robustness. Their investigation examines how model vulnerabilities change across different economic conditions, using a regime-aware evaluation framework that segments data by volatility measures as proxies for macroeconomic stress. The startling findings show that while models maintain constant predictive performance across economic conditions, their adversarial robustness varies significantly. During stress periods, models exhibit amplified vulnerability to identical attack methods that would have minimal impact during calm periods. These implications extend far beyond finance to any environment experiencing regime changes, including medical diagnosis systems during disease outbreaks, autonomous vehicles during severe weather, and recommendation systems during major social events. Wu and colleagues' work on behavioral calibration for truthful large language models addresses hallucination through uncertainty expression training, representing a significant advance in AI safety. Their approach recognizes that hallucination isn't merely random error, but a predictable consequence of training objectives that prioritize mimicking data distributions over epistemic honesty. Using strictly proper scoring rules for epistemic honesty, they demonstrate that a 4 billion parameter model can match frontier model calibration performance through behavioral training. The system teaches models to abstain when confidence is low, creating AI that acts as honest communicators rather than confident test takers. This research demonstrates uncertainty quantification as a transferable meta-skill, suggesting that behavioral calibration teaches general metacognitive abilities rather than domain-specific knowledge, opening possibilities for more reliable AI deployment across critical applications. Ichikawa and colleagues' PHOTON architecture revolutionizes sequential information processing by replacing token-by-token scanning with multi-resolution context access. This hierarchical system maintains multiple latent streams at different resolutions, with bottom-up encoders progressively compressing tokens into low-rate contextual states, and lightweight top-down decoders reconstructing fine-grained representations from compressed states. The experimental results demonstrate transformative potential, achieving up to 1,000-fold throughput improvement per unit memory while maintaining competitive quality. This improvement is particularly pronounced for long context scenarios and multi-query tasks where multiple questions require processing with respect to the same extensive context. The work proves that attention limitations are architectural artifacts rather than fundamental constraints, suggesting new possibilities for scalable language technology that could democratize access to advanced AI capabilities. Future directions in machine learning reveal several critical paths for continued development. The growing emphasis on uncertainty quantification for safe AI deployment indicates that future research will increasingly focus on developing systems capable of operating safely in uncertain or adversarial environments. Domain-specific knowledge integration for interpretable systems represents another major trend, with researchers finding innovative ways to incorporate physical laws, expert knowledge, and domain constraints into their models. Continued architectural innovation promises further efficiency breakthroughs with hierarchical processing, adaptive computation, and specialized designs for different modalities becoming increasingly important. Learning from limited feedback in data-scarce environments may become crucial as machine learning expands into domains where perfect supervision is unavailable or expensive. Finally, causal inference integration for cause-effect reasoning capabilities will enable AI systems that understand and reason about causal relationships rather than merely identifying statistical patterns. Our AI synthesis and review process maintains transparency in research analysis methodology to ensure accuracy and reliability. This synthesis was created using GPT and Anthropic Claude Sonnet 4 for comprehensive analysis of the research papers. Text-to-speech synthesis is powered by OpenAI voice generation technology for natural audio delivery. Visual elements are generated using Stable Diffusion for consistent presentation aesthetics. All content undergoes review by human experts for accuracy and completeness. However, potential oversights may exist in our analysis, and we provide all original references for independent verification. This transparent approach ensures that our audience can access both our interpretation and the original research for comprehensive understanding of these groundbreaking developments in machine learning. Subscribe and stay at the AI frontiers by joining our community of AI researchers and enthusiasts. Subscribe to our YouTube channel for weekly research updates that bring you the latest developments in artificial intelligence. Our content features deep dives into cutting-edge AI developments and breakthroughs, providing expert analysis of papers that matter to the future of technology. We foster interactive discussions on emerging trends and methodologies, ensuring you're first to discover the innovations reshaping our technological landscape. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed about the research that will define tomorrow's AI capabilities. Join us as we explore the boundaries of what's possible in artificial intelligence and machine learning. The future of learning is here, and today's research journey reveals key takeaways that will shape the next generation of artificial intelligence. Efficiency and reliability emerge as fundamental research challenges, requiring innovative solutions rather than simple scaling approaches. AI systems must be designed for robustness from the ground up, incorporating adaptive mechanisms that can handle dynamic environments and regime changes. Domain knowledge integration creates more trustworthy AI by combining data-driven learning with mechanistic understanding. Uncertainty quantification enables safer AI deployment by teaching systems to express their limitations honestly. The next generation of AI will be more efficient, more reliable, and better aligned with human values and needs. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer, this video uses archive-preprint-server.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive-preprint-server.org.